All right, good morning, everyone. I'm just going to be picking out problems from review packet number 3. But I'm going to try to pretty much go in order of some of the problems that I feel like will be good for us to do. But you can chime in at any point if you see a problem that or a concept that you want me to go over. Okay. But let's just start with number 2. We got limit as x approaches -11 from the left side of -11. Our expression, square root of x plus 19 minus root 8 all over x plus 11. So the first thing that we do, if we see a limit problem and we see a real number, we just go ahead and make that substitution into the expression, right? We don't pay attention to that one-side limit. We don't do decimals. We always just deal with the whole number to begin with, or the integer to begin with. Okay, so -11 plugs in for x. We get -11 plus 19, which is root 8. Root 8 minus root 8 is 0. -11 in for x, we get -11 plus 11, which is also 0. So 0 over 0. That tells us that we have an indeterminate form. And if we have an indeterminate form, we know there's something about the graph that we know. That there's a hole in the graph, but the limit exists. Okay. We don't know what that limit is yet, but we know that through our next set of efforts, we're going to be able to arrive at a real number answer. And that's our goal. So with this type of problem, we have actually 2 ways of going about. One way is I see radicals in the numerator, so I can either go through conjugate method. But then if we have 0 over 0, we also have L'Hopital's rule available to us. And the nice thing about L'Hopital's rule is it's kind of like this umbrella rule that can handle a wide variety of limit problems, as long as you know how to find a derivative. And you get 0 over 0, you know L'Hopital's can kind of handle. Now, these specific algebraic methods are very, very narrow in terms of what it can handle, right? There's a rule for every, but L'Hopital's rule can handle a lot more. But we'll go through both methods, and you can decide and choose for this problem how you want to go about doing it, if you see it. So conjugate method, I'm going to take my numerator expression multiplied by the conjugate. Conjugate term is just the exact same expression as my numerator. I'm just changing the sign. So multiply by, instead of a negative in between, I'll multiply by a positive to get that opposite sign to show up. And the advantage of the opposite signs is we know that things will clean up nicely when we FOIL. Okay, so when we FOIL, we're just going to FOIL the numerator. We're going to leave the denominator alone because it's already displaying what we want to show up in the numerator. If the x plus 11 is showing up in the denominator, we want an x plus 11 in the numerator because we're hoping to cancel some factors out that's causing this to show up. So as I FOIL, my first set of expression gives me x plus 19. My next set of expression terms gives me -8. So I get x plus 19 minus 8. 19 minus 8 is 11. So my numerator expression is just x plus 11. And that's exactly what I was hoping for, right? We're hoping for these two to match and cancel out because we now know what's causing that 0 over 0. Okay, so we remove the hole. And we're left with a simpler expression that hopefully will lead us to a real number. 1 over root x plus 19 plus root 8. And our final step is to reevaluate our limit. Replace x with -11. We get 8, which is under the square root. So square root of 8 plus square root of 8 is 2 root 8. Okay, any questions with conjugate method? So this method is perfectly fine, but just want to show you, we also have another option, which is L'Hopital's rule. Because we're getting 0 over 0, and we know derivative methods, we're going to take the derivative of the numerator, take the derivative of the denominator, and then reevaluate and see if we get the same answer. So the first thing that I did was, before I found the derivative, I just rewrote my expression, because I know that variable involved, I have to use some sort of a power rule, chain rule. So rather than staring at a radical, I'm going to rewrite it using a rational exponent. So x plus 19 raised to the 1/2 minus root 8 over x plus 11. I'm ready for my derivative process. So I'll go through chain rule, outside's derivative times inside's derivative. So outside's derivative, parentheses to the 1/2. Inside's derivative, I got to handle that x plus 19. So here's my derivative. Parentheses to the 1/2 becomes 1/2 parentheses to the negative 1/2. And then in the separate region, I need to find x plus 19's derivative, which becomes 1. Okay, we keep going. Negative root 8, that's a constant, so constant goes away to a 0. So that completes the derivative of my numerator portion. And I'll repeat the same process to find the derivative of my denominator portion. X derivative is 1. 11 goes to 0. So I have a derivative version of my expression. So now I'm going to reevaluate. So if I reevaluate, I should be able to get my way down to a real number. So replace x with negative 11. I get negative 11 plus 19 raised to the negative 1/2. This becomes 8. 1/2 times 8 to the negative 1/2. The same thing as pushing that 8 down to the denominator, making that 8 a radical. And we see we get the same answer either method. You can decide which one to use. But it's nice to have L'Hopital's rule in your back pocket, because most limit problems, if not all, as long as you get 0 over 0, it's a great way to work out a bunch of problems that otherwise would have difficulty in terms of other methods to use. All right, any questions with number 2? Good. All right, next problem I picked out is number 12. So number 12 says, find the point on the graph y equals root x between 1, 1 and 9, 3, at which the tangent to the graph is the same as the slope of the line through 1, 1 and 9, 3. So it doesn't say it, but the description is basically that of mean value theorem. Mean value theorem is where we want to find out the slope of the tangent is matching the slope between the endpoints. So here is mean value theorem. F prime of C is equal to f of B minus f of A over B minus A. Slope between the endpoints can be found on the result of this calculation. Tangent can be found by, can be achieved through the derivative, so we know how to involve the derivative. We have our two endpoints, our x values between 1 and 9. They give us the order pairs. So we don't have to do any finding of the y values. We can go directly into finding slope. But here's a visual example of what we're trying to achieve. You have your slope between the endpoints. We're going to find out that slope first. But we know that somewhere on the curve, there's going to be an exact slope of whatever we see here. And our goal is to figure out the location of that particular rate of change on the curve. And to achieve that, we're going to set the derivative equal to that slope. And then turning around and finding out that location. So first, let's find the slope between the endpoints. That's the first thing we do. Take our order pairs, change in y over change in x. And we'll be able to work our way down to 2/8, which is 1/4. So this is our first goal, trying to figure out what is the slope target that we're after. So we know that we're trying to target a slope of 1/4, and now we're going to use the derivative to help us locate that particular slope. So let's move on to f prime. To find f prime, I need to find the derivative. To find a derivative, I'm going to first rewrite this equation using rational exponent. So rewrite it as x to the 1/2. Power rule, 1/2 x to the negative 1/2. Which is really 1/2 root x. All right, so we have the two pieces now that is going to help us get to our answer. We have the slope target, and we have the formula that's going to connect the slope value to the order pair or to the location. So we set these equal to each other. So 1/2 root x is equal to 1/4. Cross multiply. Solve for x, square both sides. I get x equals 4. So now we know the x value location, right? But it's a guarantee that this will show up as a value between 1 and 9. And so that's what this value is, right? It is value of 4, but then the last step is it's asking for the order pair. So if I want to find the order pair, then I need to take this x value, put it back into the equation, and get the location of that point. So that's why if I plug 4 into root x, I get square root of 4, which is 2. So that's how I get my order pair for 2. Questions? You guys good? All right, let's look at number 19. Oh, sorry, I skipped. Let's do 14 first. We'll do a derivative practice here. 14 says, consider the curve x plus xy plus 2y squared equals 6. The slope of the line tangent at the point 2, 1 is. So basically, we're just going to find the derivative and then plug in the value to get from a derivative to a slope. Okay, so I'll put this on a separate page here with the problems written out. So look at how this equation is set up. Can we identify what process is involved to first find the derivative? What do we see? Product rule and implicit. Yeah, these got a couple of y's stuck inside the equation. Yeah, so product rule and implicit. Product rule because of the x times y, right? There's no way for us to resolve that. We have two different variables that are multiplied together. So we have to keep those separate and understand that they're being multiplied, and the way we involve derivative of something multiplied, we have to go through product rule. Implicit because we have y's showing up inside the equation. So we begin our derivative process. All right, so x becomes 1. For the xy portion, we do f prime g plus fg prime. So x becomes 1. We keep the g function back to f, and then y's derivative is dy dx. All right, keep going here. 2y squared becomes 4y dy dx. And then the 6 is a constant, so that constant will go to 0. Okay, let's just go ahead and solve for dy dx, because once we can get dy dx by itself, then we can involve the order pair. So just going to rearrange my terms, get my dy dx variable on the same side so that I can work towards factoring it out. Okay, the x and the 4y, because there's dy dx attached, that's going to stay on the left side. The terms that have no dy dx, well, I'm going to just subtract it over to the other side. Factor the dy dx out. Divide the parentheses over. And that leads to our derivative equation. Once we have our slope formula, we're now ready to involve the order pair. So we'll put 2 in for the x, put 1 in for the y. Typically, the notation that we use is dy dx with a vertical bar and 2, 1 to indicate I'm about to evaluate a derivative at a point. And this will take us to a real number, and that real number will match one of the answer choices, -2/6, which is -1/3. I'm going to extend the problem a little bit. Let's say I ask you to find a tangent line equation. So I want to show you that despite this not being a function, we still find it the same way. Take the slope, take the order pair, and then from there build your tangent line equation. All right, any questions with 14? Okay. Let's look at number 19. This is a particle motion problem where there's a restriction on time. T is greater than or equal to 0. Position function is given. It's asking when the particle is at rest. So I'm going to extend the problem a little bit and ask when is the particle not only at rest, but then part B, when is the particle moving to the right? So let me put this on a separate sheet here. So here's our position function. This particle is moving along the x-axis. Any t-value we put in will give us a number. That number will tell us where that location is of the particle on the x-axis. For part one, we're going to figure out when is the particle at rest. And the strategy to do that is get to the velocity and set the velocity to 0. And velocity is basically the first derivative of position. Okay, so we'll do that. And then from there, we can build our velocity sign line. And from the velocity sign line, once that is populated, we can determine the interval where the particle is moving to the right. So when we populate the velocity sign line, we're going to have plus and minuses. And plus is going to indicate interval moving right. Negative would indicate interval moving left. All right, so let's do part one. Find when the particle is at rest. Particle is at rest when velocity is 0. To get to velocity, we need to find the derivative. To find the derivative, in this case, we have to go through quotient rule, right? So f prime g minus fg prime all over g squared. Try that. All right, so any questions up to this point? Velocity cleaned up all the way. So now the next part is finding when particles at rest. So we know we have to set velocity equal to 0. But do we set both the numerator and denominator equal to 0? What do you guys think? Just the numerator, good. If we set the denominator equal to 0, that's going to tell us when the velocity is undefined. That's not quite what we want. We want to find out when the velocity is 0, so just the numerator. So if I set 4 minus t squared equal to 0, I get plus or minus 2. But it's already established at the beginning that we're dealing with a domain of 0 and greater. So negative is out. We only have positive 2 as a valid answer. So particle is at rest when t equals 2 because velocity is 0. And I'm going to extend the problem by asking when is the particle moving to the right. So let's create our velocity sign line. There's only one critical point at 2 because that's when velocity is 0. But we're going to put another number onto the sign line. Do you know what that number is? 0, yeah, because that's the starting point that's provided for us at the beginning. So we'll do 0 and 2. So we're going to start off with 0 and 2. And then the next step is we want to populate on either side of our in our two intervals. So I'll choose two numbers. I'll choose 1 to the left of 2 and 3 to the right of 2. Evaluate the velocity at 1 and 3. So let's do 1 first. If I put 1 in for t, I get 4 minus 1, which is 3. Over anything squared is positive, so positive over positive is positive. Okay. Evaluate 3, 4 minus 3 squared, that's 4 minus 9, which is negative. Negative over positive is negative. So there's only one interval of positive, so my answer is going to be from 0 to 2. But there's a subtle addition that we have to include, and it's the fact that 0 is on there because it's a starting point. It's not on there because velocity is 0. And 0 is part of our domain. So maybe the object is already moving at 0, so we need to test 0 as well. So if I plug 0 in for t, I get 4 minus 0, which is 4. 4 over 16 is positive. So my interval is going to have a bracket at 0 because it's already moving at 0. We don't have it at 2 because we know 2 is a resting time period for this particle. But 0 is not a resting period because it didn't show up when we were setting velocity equal to 0. So it's bracket at 0 and not parentheses. 1, because it's moving to the right, and second, because it's part of our domain. So it's a valid point to test. And the reasoning is because velocity is greater than 0. Okay, any questions with 19? All right, let's do 25. This is a related rates problem. All right, so here's 25. In the triangle shown, theta is increasing at a constant rate of 3 radians per minute. At what rate is x increasing in units per minute, where x equals 3 units? I know that related rates, I'm expecting a bunch of d over dt's, but we always have to start with an equation, right? In this case, we see theta, so we know we're choosing between sine, cosine, and tangent. So based off of theta and the location of the x and the 5, what do we want to use? Sine, cosine, or tangent? Sine, yeah. So we start off with sine theta is equal to x over 5, which is same thing as 1/5 x, and we can move to get to the derivative, right? So if we find the derivative, sine theta becomes cosine theta d theta dt, right? We're expecting time variable differentials to show up. And then 1/5 x becomes 1/5 dx dt. All right, so if we go back and read the problem here, it's saying that theta is increasing at a constant rate of 3 radians per minute. So we know that that's d theta dt, right? So we have information about d theta dt. We also have information about that we're looking for dx dt because it says at what rate is x increasing. So we know dx dt is the variable in question. And then when x equals 3. So I can also gather that information. Okay, so back to my derivative equation. I know that my answer is going to come from this equation. D theta dt, we have that provided for us, so we know we can replace that with 3. Dx dt, that is the variable that we're ultimately trying to solve for. So that shows up, that's good. But the one thing that we have to resolve is that cosine theta. So we want to find a fractional ratio that we can replace cosine theta with. So we're going to create a second triangle, and the second triangle that we're going to fill in all the side values so that we can determine the ratio at that moment in time. So I have x equals 3. So I'll put 3 into that vertical height component. If I have 3 and 5 in my triangle, I can figure out the third side using Pythagorean theorem, or if we recognize this as a Pythagorean triple, 4. So now that I have all 3 sides accounted for, now I'm going to figure out what is cosine of theta. And cosine of theta is just adjacent over hypotenuse, so 4/5. So now we have everything that we need, right? We have cosine theta, we have d theta dt, and then the only variable that's missing is dx dt, and that's what we want to solve. And the rest is just plugging in. Okay, any questions, 25? Let's see what else. Let's look at 35. This is practicing reading a derivative graph. Okay, f prime is the derivative of function f. Which of the following is true? So before I look at my choices here, I'm just going to see if I can gather information from my slope, my derivative graph, and see if I can create a slope sign line based off of, and the concavity sign line based off of that. So I'm going to start off by marking what I'm looking at, right? Anything above the x-axis is going to be positive slope. Anything below the x-axis is going to be negative slope. Anything on the x-axis is slope 0. And then for my second derivative sign line, I know that the peaks and valleys of my graph will be the points of inflection of the original. So I redrew the graph and I just started to gather some information to put it onto my slope sign line. So I'm going to first start off by picking out my x-intercepts. So -2, 1, and 3. -2, 1, and 3. And then with my endpoints are from -3 to 4. And then with each subinterval, I just want to know what the slope of the original graph is going to be. Is it positive or negative? We don't want to look at the slope behavior of f prime because that's not what it's not going to give us the information that we want. The slope values are sitting at the physical locations, so we just want to look at the location. Here, we may have some various values of positive slope, but these are all positive slope because it's above the x-axis, so we just want to make a general observation that the original graph is going to be rising in that interval. Between -2 and 1, between -2 and 1, all these are values below the x-axis. All these are slope values below the x-axis, so that indicates negative slope. We'll make a general observation, it's negative slope. From -1 to 3, still below, so negative slope. From 3 to 4, positive slope. And these arrows are helpful because this is actually going to tell us how the graph is going to rise and fall and where it's going to rise and fall. So it's going to rise to a relative max at -2. It's going to fall and flatten out, but neither max nor min. Continue falling. Hits a relative min at 3. So I'm just going to make a note. I'm expecting relative max at -2 and a max and a min at 3. I'm also going to create a second derivative sign line. And second derivative sign line, I'm now going to pick off the points of inflection to populate my second derivative sign line. And then from here, now I'll look at the slope. Wherever the slope of f prime is decreasing, that indicates where the slope of my original graph is becoming more negative. And wherever my slope is becoming more negative, that's going to translate to a graph that's going to resemble a portion of this concave down shape. Okay, we look at our second interval from -1 to 1, positive slope. This is where my original graph is going to exhibit a slope becoming more positive, even though it's all negative slope, but it's concave up. Okay, from 1 to 2, negative slope is going to indicate concave down. And then positive slope indicates concave up. So we expect 3 points of inflection. If the problem is asking for rise and fall, max and min, points of inflection, we can find all that by pulling from our slope and concavity sign line. So now I think we can answer our question, right? F is increasing from 2 to 4. We're just looking at our sign line and see if it's in agreement. Well, from 2 to 4, portions of it is increasing, but not all of it, right? So we know we can eliminate choice 1, right? It's not consistent with what we gathered. Choice 2, relative min at -2. Well, we know there's a relative max at -2, a relative min at 3, so that doesn't, that's not matching with what we know to be true. And the third statement, our function has an inflection point at 1. That is true. We found an inflection point at 1. So our answer choice is C, right? C only, 3 only. All right, I also want to show that, if you're given the derivative graph, maybe you'll see a problem where you're asked to match to the original f of x graph. So why don't we just sketch what the graph could look like based off of the sign lines that we created. So I'm just looking at my sign line. Our graph may not be in physically the same location, but all of our graphs should have a similar shape. I'm expecting a relative max at -2, so I'm just going to create a graph with that behavior. So at -2, I'm just going to locate a point that I'm going to target as my relative max. Typically, I like to pick a point that is higher on my coordinate plane. At 1, I know it's neither, so I'm just going to pick a point that is where I can decrease, but I can have some more room to decrease. At 3, I'm expecting a relative minimum, so I'm just going to purposely exaggerate and pick a point really low on my coordinate plane. Okay, so that's all I want to do for now. I'm just going to sketch my graph and worry about my concavity later. Okay, so rises to a relative max, levels off, falls to a relative min, and then rises after that. At least I have something to work off of. And now I can work in the curvature within my graph. I know my points of inflection at -1, 1, and 2. So wherever my graph lands at -1, I'll highlight that point. Wherever my graph lands at 1, I'll highlight that point. And then at 2, I'll highlight that point. So from dot to dot, I'm going to over-exaggerate my concavity. So concave down from -3 to -1. -1 to 1, concave up. 1 to 2, concave down. And then from 2 to 4, concave up. Okay. If you can put this level of detail into your f of x graph, then it'll be easy for you to match whatever answer choice is in front of you. Okay, a couple minutes. Couple things here. Remember that if you're asked to find the derivative of a trig function, make sure you rewrite it, especially of ones that may involve chain rule. So once you get it into that form, you can see that there's outside portion, inside, and inner. And then we just take turns with each derivative, make sure that they all go in a separate space and not within each other. So outer derivative, bracket squared becomes 2 bracket to the first power, cosine parentheses becomes negative sine parentheses, and 2x becomes 2. And each of the brackets and parentheses are filled in with the original parts of the problem. And I did a little bit of cleanup. I pushed the coefficients in front, and that's answer choice B. Okay, finally, just want to go over the steps for linear approximation. So let's say I gave you an ordered pair, 3, 4, slope is 9, approximate y of 3.2. So just understand that linear approximation, most of your effort is going to be trying to get that tangent line equation up and running. So tangent line equation, that means I need to find point and slope. Sometimes you may have to find the derivative and evaluate the derivative, but this problem already gives you everything that you need. So just do change y minus y1 is equal to m times x minus x1. Once you find your tangent line equation, then I'll do a little bit of rearranging. I'll add 4 to both sides, get that y by itself. And once that y is by itself, then you're almost there. 95% of the work is done. The last part is just to evaluate that decimal, put that 3.2 in for the x, and whatever the result is, that's your answer. All right, any questions? All right, I have a health session this afternoon, tomorrow morning, afternoon, and Thursday morning, 7:15. So I encourage you guys to continue working through review packet 3, and if you want to get some more additional practice, pick out those problems from packet 1 and 2. All right, have a great day. Good luck with your exams.